Okay, awesome. Thanks so much for having me. I'm super excited to be presenting this morning. Our work is social connectedness and the geographic spread of COVID-19. This is joint work with Teresa Kuchler and Johannes Strobel. We're professors at NYU Stern. I'm a research scientist there at Stern. And I think it's important to say at the outset that our backgrounds are in economics, not epidemiology. And so our goal in this work is really not to make some state of the art epidemiology model. It's much more to just provide a proof of concept using a really interesting set of data that we've been studying in an economic context and that we think could be useful for predicting and tracking the spread of COVID-19. So our motivation stems from a pretty straightforward idea that if you want to determine a region's risk of an outbreak for a communicable disease, it's valuable to know which individuals are likely to physically interact. And these interactions are shaped by social connections. You're more likely to interact with individuals you know than individuals you don't know. The challenge is that the geographic structure of social networks is really difficult to measure, especially on a national or a global scale. But the solution we're going to introduce is this aggregated measure of connections between region pairs that uses de-identified data from Facebook. So I think as everyone here knows, Facebook is a massive online global social network. It has 2.5 billion monthly active users globally, and around 250 million monthly active users in the US and Canada. We think it captures real world connections better than some other online networks for a couple of reasons. First, there's a limit on the number of friends you can have. It's 5,000. So you have to be somewhat selective in the individuals you're adding. And second, it requires the consent of both parties to form a friendship link. So, unlike something like Twitter, for example, where these unidirectional links to celebrities where you follow a celebrity is common, here you both have to agree that you want to share and see each other's content. And that these connections represent real world connections is really important for the argument that we're going to make in this paper, because we're going to say that these connections on Facebook are really a proxy for real world connections, the kind of connections that could lead to physical interactions and the spread of COVID-19. This measure of connectedness is going to be called the Social Connectedness Index. It was actually first introduced in a paper in 2018 by Mike Bailey, who's a research scientist at Facebook, and my co-authors on this paper, Johannes and Teresa. And it's a pretty straightforward metric. The numerator is the number of Facebook connections between users in region I and region J. And the denominator is the number of the product of the number of users in region I and the number of users in region J. So it's a normalized number of Facebook friendship links between two regions. And it captures the relative probability of friendship between Facebook users in regions I and J. So one easy way of thinking about this is that if you see a doubling in social connectedness, a doubling in SCI, it corresponds to a doubling in the likelihood that an individual in region I is friends with some other arbitrary individual in region J. There are a few works that already use this measure. There's one that we think is quite relevant for this example by Koven and Gupta in 2020. There they look at patterns of mobility for New Yorkers during the pandemic using cell phone data. And they find that individuals in New York or counties that have stronger social connections using this SCI measure to New York are more likely to be destinations for New Yorkers fleeing the pandemic in those early months of March and April. So this is kind of like, in some ways, in this small case, a smoking gun for the argument that we're trying to make. This argument that these social connections are predictive of people's patterns of movement during the pandemic. Importantly, in the spirit of this conference, and just for us as researchers, these data are widely available. You can email this SCI data at fb.com to get access. It's a pretty straightforward process. You submit a one-page proposal, and there's over 500 research teams using the data already. So, again, in the spirit of this conference, is something that we're really excited about, that we can bring this aggregated measure to so many other researchers. And you'll get access to the in a Dropbox, you get access to the code for this paper. So our first set of analyses are going to be these hotspot case studies, and our motivating question is going to be whether areas with stronger social ties to early COVID-19 hotspots have more confirmed cases by the end of March. We're going to look at two hotspots. The first is Westchester County in the U.S. It contains New Rochelle, which was a highly publicized early U.S. outbreak where they called in the National Guard in early March. And it's also home to many wealthy residents who might have fled. So there were a number of newspaper articles, and the governors of Rhode Island and Florida were publicly lamenting how all these wealthy New Yorkers and Westchester residents were coming to their states and spreading COVID-19. So this provides a sort of plausible vector for how COVID might have spread along these social connections. Our second case is the Lodi province in Italy. It's also an area with one of the earliest Italian outbreaks. It's part of the Lombardy region, which is a destination for a lot of workers and students from southern Italy. So there were, again, a lot of articles in the Italian press about how these workers were traveling from the north to the south during the early stage of the pandemic. The government was actually trying to do a lot to restrict this flow of movement. Importantly, in all of our analyses, we're going to control for geographic distance. We want to make the argument that this measure of social connectedness is provides additional predictive value above geographic distance alone, and this measure is going to correlate with both geographic distance and the spread of COVID. So we're also going to control for population density, median household income, and we're going to exclude regions within 50 miles or kilometers in this analysis. Again, this is an area in which you might be interacting with people even if you don't know them personally. So you might see them at the grocery store, you might encounter them in public places. So we really want to try to pick up this additional predictive value from social connectedness. This is just a map of social connectedness from Westchester County to every other county in the United States. So the red one there is Westchester, and then darker colors indicate higher levels of social connectedness. So you can see it's most strongly connected to places in southern New York and New Jersey, places that are physically close by. But there's also some patterns that physical proximity alone wouldn't predict. So you can see strong connections to the southeast coast of Florida, for example, and in central and western Colorado. And we think this has to do with these destinations being popular vacation spots for residents of Westchester, places where they might have second homes, on the coast of Florida and in these ski resort areas in Colorado. And so this is just a map of COVID-19 cases per 10,000 residents on March 30th. And you can kind of flip back and forth between the maps and see some similarities and differences too. Notably, the two areas I pointed out on that last slide, the east coast of Florida and central and western Colorado, both seem to show up on these maps. There's also some trends, that it looks like social connectedness alone wouldn't predict. So you can see the hotspots in Louisiana and Washington. But there does seem to be, at least to the naked eye here, there does seem to be some sort of correlation between these two maps. So we'll look at this more formally using a bin scatter. So here we split the data into 50 equal-sized bins based on that log of social connectedness on the x-axis, and then we plot the average of the x-axis measure against the y-axis measure, COVID-19 cases per 10,000 people. We see the strong, positive relationship between connectedness to Westchester and cases per 10,000 people without controls in the left panel, and we see it persist when we add our controls in the right panel for population density, geographic distance, and median household income. So this, this, at least in this one case study, this gives us some support for that argument that we're trying to make, that social connectedness predicts the spread of COVID-19. This is analogous results for that other province, Lodi in Italy. And again, we can see strong social connectedness in a number of COVID-19 cases in nearby areas. We also see on the east coast of Italy, there's the Rimini province, which is a popular tourist destination that has both strong connectedness and a number of COVID-19 cases. We can actually see there's a little bit stronger social connectedness in southern Italy than there is cases on March 30th. And we hypothesize maybe one reason for this could be that the restrictions of the Italian government on mobility actually was to some degree successful in preventing the spread to southern Italy. Nevertheless, in panels C and D, you can see that this positive relationship between connectedness to a hotspot and COVID-19 cases at the end of March persists. So moving on, we're gonna next ask whether social connectedness has a systematic predictive power above geographic distance. And we're going to use this using a time series in the US because the sort of center of the pandemic has shifted so much, we're able to do this. We're going to construct two key measures. The first is social proximity to cases. So this is cases weighted by your social connections. So if you're more socially connected to areas that have more COVID-19 cases, then the magnitude of this measure will increase. And similarly, we're going to make a measure physical proximity to cases, where if you're closer to other counties with many cases, the magnitude of this measure will increase. So sort of a similar idea, but the first picking up our measure of social proximity, the second one using physical distance alone. And we're first going to look at this in a pretty straightforward regression framework. T here is a 2-week time period between March 31st and July 20th. The left-hand side variable is the log in the change of cases per 10,000 residents. And the right-hand side is going to include measures that are lagged by 1 and 2 time periods. So we're taking these measures from the past and trying to predict the future, the change in cases in the next period. The right-hand side measures are going to be the actual change in cases in the past. So do changes in cases in one period, predict changes in cases in the next period, as well as our two new measures, social proximity to cases in the past 2 periods and physical proximity to cases in the past 2 periods. So the question, the motivating question here again is, does this measure of social closeness to counties with a number of cases in the past then predict your cases in the future? XI is going to include other controls for population density, median household income, and state. This is the results of that analysis. So each column here is one of those 8 2-week time periods. The top row is really, I think the most important thing here. We see that the coefficients on social proximity are always positive and significant for each of these time periods. Even in the presence of our measure of physical proximity and in the presence of our measure of actual cases in the past. So it looks like, social proximity to cases, it is always a significant predictor. This 2-week lag SCI weighted measure. We find this pretty compelling evidence because the center of the outbreak, like in each column, the places most affected look pretty different. It's New York in the first column. It's then it moves to Southeast Michigan, throughout the Midwest and to the South. So it's very different places, which gives us a little bit more confidence that there's not some omitted variable, driving these relationships, like something that could have happened in the case study analyses. But while this provides some confidence for us, we also want to try to make actual predictions. So for each time period, what we're going to do is we're going to build really simple models with that same setup we discussed 2 slides ago, the 1 and 2 time period lags. And we're going to train the model. We're going to exclude the first week. We're going to train a model starting on that first week to then predict the next week. And then for the week after that, we're going to train a model, estimate our coefficients using the first 2 weeks and use that to predict in the third week and so forth. So we're using all the past data we have to try to train a model to then predict the next week, a true test, training set and test set exercise. We're going to do 2 different model specifications. The first is just exactly the same as the regression I showed you 2 slides ago, a simple linear regression. The second is going to be a random forest, where we'll put all of these measures as inputs into a random forest. We're going to get a little bit more predictive power that way. This is the results of that analysis. So the left panel here is the root mean squared error from the linear regression model. The right panel, right 3 columns, are the root mean squared error from that random forest model. The first column in each panel is the root mean squared error from a model that just uses our 2 periods of lag measures for previous cases, physical proximity to cases, population density, and median household income. And then in the second column in each panel, we're going to add social proximity to cases. So this is, again, our measure of interest. In the third column, we're going to show the difference between the 2 measures, the 2 root mean squared errors from the 2 models. So negative signs in columns 3 and 6 indicate that our predictions are actually getting better because we're adding this measure of a social connectedness. So and we do see that in most columns, this measure is improving our predictions. The 2 exceptions are the first 2 weeks with the linear regression model, where we have relatively less training data and our predictions are generally worse. So this again, unlike an increase in R squared that I showed you a couple slides ago, this makes us more confident that we're actually improving real world predictions. So social proximity to cases is reducing the root mean squared error predictions over and above information about geographic distance to COVID-19 cases alone. So
Dominic, you have 5 minutes left.
Okay, thank you. So this social connectedness index is we think is a really unique measure to quantify things that are important for the spread of communicable disease. And in this paper, we do 2 simple analyses. Like I said, we're not epidemiologists, so they're sort of straightforward. The first, we looked at these hotspots, and we saw that regions that were more connected to early hotspots in the US and Italy have on average more cases by March 30th. In the second, we did this prediction exercise using a time series in the US, and we found that the inclusion of social proximity to cases improves prediction of COVID-19 spread above our measure of a geographic distance to cases. So the main purpose of this work is really to highlight opportunities for future researchers. The data are available for US counties, for Europe NUTS2 and NUTS3 regions, and for much of the rest of the world at the GADM1 or GADM2 level. It's a pretty simple proposal process, submitting to sci-data@fb.com. And like I said before, there's already more than 500 research teams using the data. I do want to save some time for questions, but I think this data is like super cool. So I have a couple more maps just to show you, the extent of the data and sort of some of the things you can do with it. Maybe I'll skip through this a little. We're going to look at San Francisco and Kern County. San Francisco is a wealthier county. Kern is a little bit less wealthy, has a larger Hispanic population, also in California. This is just a map of San Francisco to North America, of every county in San Francisco to places in North America. And this is a map of Kern County to places in North America. So you can kind of flip back and forth between the two, and you can see the differences and similarities between the two. San Francisco much more connected to areas in the East Coast. Kern much more connected to areas close by in Mexico. And then you can bring this to with pretty fine granularity to the global level. So this is San Francisco to the whole world. You can see strong connections to Europe, from Mongolia, and much less strong global connections from Kern, but stronger connections to Mexico. So you can flip back and forth and sort of see how cool this data is. So with that, I have one more example, but I'll hold off because I want to have time for questions. So thank you so much for having me, and I appreciate it.
Very cool work. Can you see the Q&A, or otherwise I can just ask the question?
I cannot see the Q&A. Okay. So yeah, thanks. So
you have one question that came in asking about the connectedness to airline hubs. Kind of the example of San Francisco would point to that as well. Have you thought about that or looked at travel?
So we've looked a little bit in Europe. There's this interesting European data on passenger and freight train travel and how that correlates with social connectedness in Europe. We haven't really looked at airplane travel. That's a really interesting potential avenue for research that we haven't thought about. But in Europe, we do find that social connectedness correlates with patterns of train mobility. People go and visit their friends who they're socially connected to. So train travel is correlated with social connectedness.
That makes sense. All right, great. Well, thank you very much.
Yeah, thanks so much for having me.